All right, so no more test before the exam, but you still got your lab number 4. I'll release it pretty soon, maybe early next week. So that would be something not to do with the celebrity, but something kind of interesting for you to also look at. I will maybe draw some remarks, maybe maybe around the submission deadline or after that, just give you some perspective about lab number 4. It's kind of interesting lab. Pretty simple, straightforward, but just pay attention to the logic that we are using in that particular lab. And I think at this point, I think we are about less than 1 month away for the exam. So you may want to start doing 2 things. Number 1, you may want to start crafting your data sheets. There will be 1 site data sheets allowed. You can computer type or handwritten, doesn't matter. Okay? You can choose whichever way you like. You can put anything you like on the sheets. Can be screenshot, can be proof, can be inference rule, or can be anything you like. Okay? You can also collaborate with your fellow students to really make the sheets. That's okay. But just make sure bring your own copy on the exam day. That's number 1. And number 2, I think it would be very wise to actually start going over the materials about a course. Especially, it's been a while since we touched upon the math review slides. You may want to take a look at that. And also, I think in the coming 5 or 6 classes left, we're also going to dive also deeper into the bridge controller. So things will get just more and more kind of sophisticated. So you definitely want to also catch up, with the lecture. So I would suggest just plan your study steadily for that, and our exam will be on the 11th of December. So I think that's pretty quick, but we definitely can schedule some review session after the last day of class. I'll do some survey just to see which day you guys might prefer. We'll see. Question?
So regarding the final, and I know that you mentioned the math review slides, will we potentially have questions about just like the content of math reviews, like functions or sets, relations, things like that?
Oh yeah, sure.
Will it be like all applications, or they in the content of breaking
Right.
controller?
So the question was, as for the math review slide lecture, like a contest, can you be just asked about purely mathematical question? Yes, it's possible. A little bit like for your written test 1, right? Just purely on the math. Another type would be more like applying maybe math itself to maybe a bridge controller, or I'll give you guys some example question for the sample exam. Not exactly like a sample exam, but some example question. That one there is more like a refinement or like a system model using functions again. So you can use that as another example to practice. Yeah. Okay?
So do we have 2 more lab 5 or only lab 4?
I believe you only got 1 lab left.
So lab 4 is the last one.
Lab 4 is the last one.
And for our lab mark, is it possible to have a TA updated, like they should already, if we should already get 3 points if we submit anything?
Yeah, so normally I only kind of release the e-post file, for your lab mark after around the time I kind of calculated like a course grade. Because you can pretty much assume if you have already submitted your work before the submission deadline, you're safe to assume, right? I'll try to see if I can make the e-post file maybe a little bit earlier, so just in case. Yeah, I'll try to see, at least before the exam day. How about that? I'll try, yeah. But for your lab submission, don't worry. As we said in the policy, we're not going to grade your best attempt. Just make sure you, as long as you submitted your work before the submission deadline, you're fine. Okay, for the percentage. Yeah.
If we were to solve entire sequence proofs on the final, does the order in which we apply the inference rules matter? I mean, as long as they're of course applied logically.
Yeah.
Because, for example, looking at the strengthening card proof, right? You could, for example, before applying the equal left-right rule, you could first apply the OR R2 rule.
I see what you mean.
And stuff like that. So it's
right.
interchangeable.
So the question was, does it really matter? You kind of follow your intuition about how to make a proof of sequence proof. Absolutely, yes. So I think for the exam, you will definitely be given maybe some sequence to actually say, okay, show that it's either provable or not provable. If that's provable, of course, you can just follow as long as your proof sequence is actually justified. Like every step is actually valid. The TA is actually going to give them some sample solution, but I'll tell them that they should also read the students each step to make sure everything's working, right? So you don't really have to worry about whether your model solution will look like just ours. Not really. As long as it's valid, you'll be fine.
Okay. Yeah. And then if we need to apply any arithmetic steps, is it better to perhaps do some sort of
Yeah. That one will be very worth actually clarifying. So for your exam, for example, if you have, let's say, let's say you already have done a bunch of work, like steps already. Let's say you want to go by arithmetic and then go to another sequence over here, and then somehow want to continue. And over here, I would say once you put arithmetic, you might just want to somehow circle or maybe put an arrow over here and say right here, and then put some justification. Right? We'll be quite flexible in terms of the format as long as it's very clear about the justification for arithmetic. Right? Or you can just put a star here, and then you can put star aside and put like that. That's also fine. Right?
And final question on sequence, sorry. Can we alternate the order in which we're solving? Because sometimes for a space, you might start vertically, but then go horizontally.
Yeah,
And then go
absolutely. I think for our double check, I want to ask just quickly, do you guys prefer like a single booklet with question followed by answer box, question followed by answer box, or you prefer just a question booklet and then answer booklet separately? Any preference?
single thing, but
Do you see what I mean?
Let's do election, let's do a petition in the in-class, like,
How about this? I can maybe, this is why I'm quite flexible, right? Maybe I can do the polling just for you guys. I just want to propose the ideas, right? You guys can choose, right? Whichever that's going to be more convenient for you. I got both versions actually, so it doesn't matter. Yeah. Okay, don't worry. I'll make some polling for you guys to fill out.
when shall we get the written test to mark?
Definitely before Tuesday's class. As I said, usually I know it's auto-graded. I already know the result, but I just want to take a 1 or 2 days. I just want to usually like to randomly pick some submission to go through, just make sure everything at least randomly is okay.
And how do we do? Do we do better than the first one?
You'll see. How about that? Okay. How about this? I was impressed. How about that?
Oh, you're impressed. Okay, that's fine.
I was impressed. Okay.
Is there 4 or 5 labs? You said lab 4 is the last one, but there's 5 labs in the syllabus.
It's 5 labs?
Yeah, 5%. This is 5% mark.
no, 5% of core labs.
Let's clarify.
That's what I checked.
So guys, let me double check. Okay, let's double check. Oh, I did say 5 labs, right? Okay, I see. Don't worry. So here's what's going to happen. 4 labs, and then still 1% each. The 1%, you just take it. Okay? It's my mistake. I should have said 4 labs, like a 1.25% each, but it's okay. Yeah. Yeah. Okay. Yeah, just 4 labs only. Question. Oh, yeah, I'm going to okay. So the example question I'm going to give to you for the exam would not be like an E-class format because that's not a format you will receive in the actual exam. I'll give you some format that's kind of more similar to what you will see in the actual exam. Yeah, you will see that. Yeah. I'll try to make it available maybe just the latest will be 1 day before the last class. That'll be the latest. So you can still take a week or so, to do it. Right? And then we can go over some of them maybe during the review session. I'll also try to host an office hour as well, for you guys. So we'll definitely have time to chat. Okay. All right, very good. Let's now do some quick recap. And then today, I want to see how much we can dive into the new events and also something called divergence or life lock. It's kind of interesting idea. Okay, we're going to talk about the difference between invariance and variance. So these are also interesting concepts. We'll see how much we can do. If not, we continue on Tuesday. Okay. Oh, sorry, I forgot to switch. There we go. Okay, so last time we basically revisited the idea about guard strengthening. So guys can just go over the intuition again. That's going to be very useful for the exam. Next Tuesday, most likely, we're going to run into another concept, which is called relative deadlock freedom. We talked about deadlock freedom before. It's really about there's at least one guard that's actually enabled, right? That's a deadlock-free condition. But in the context of refinements, it's going to be more complicated because we got guards at the concrete level. We also got guards at the abstract level. How do we kind of argue about their enableness or disenableness? So that's something we'll see, maybe next Tuesday, right? But just make sure you kind of understand about guard strengthening. That will be the very good first step. And then, so some practice for you, okay? You can definitely give it a try. And then we spoke about invariant preservation for the old events. So here we kind of so for the old events and also new event, which will be the topic for today. The new old events are those events that already exist in the abstract model. For those, we have to make sure they preserve the invariance. And similarly, for new events that only exist in the concrete model, today we're also going to show that they also have to preserve the invariant in a similar way, which can discuss them separately. So you're just going to notice for the rule, you include the axiom, include both invariants, abstract and concrete. And also include a concrete guard for any events, could be the concrete guard for ML out or for ML in. And then you got to make sure the concrete invariant in the post states will actually be preserved, right? So remember the exercise we did, whenever you got prime, you have to apply the before-after predicate. We'll do that once again today, okay? So just make sure you're comfortable with that kind of exercise of stating the post-state version of the invariance. And then commuting diagram, okay, I think the last thing we talked about on Tuesday. So very important to notice, when you actually got the concrete events over here, that's enabled. Because of guard strengthening, we know the concrete guard implied the abstract guard. So when you say the concrete event is enabled, the corresponding abstract event should also be enabled as well by logic. In that way, you know that at this particular stage, both events, almost like they're starting at the same time and be executed in parallel. And then in the post stage, we got to make sure they also satisfy the linking invariance. So we say that the abstract events simulates or correspond to some concrete events. And also the concrete event is simulated by the abstract event, right? Can go either way. Just remember, for every concrete transition we are doing, you can always find some correspondence of the abstract transition. Just get the direction right. Okay. Any questions about this? All right. So I think before the break, we should really do a little bit of just some basic stuff. I'm gonna, let me do some very quick notes just about the big picture. We're gonna talk about 2 new events today in M1, okay? So let me just start with that, just to draw some diagram here, okay, for today. And these are just the proof obligation you can actually try to prove, okay? And also invariant establishment, just the same as in M0, nothing special, okay? You can also try as well. Let's start with this quick illustration, like a heads up over here. So when we talk about events right here, so we got M0. That's our initial model. And then we know that that one there is refined by, okay? We know M1 refines M0, right? That's what the arrow really means, okay? A little bit like extends in Java, a little bit. Not exactly the same, but a little bit, okay? And here we got concrete model M1, okay? So let's revisit about concrete, abstract, old, and new, okay? So we said over here, in the abstract model, we got some old events. They already exist in the abstract model. So we got ML out. And also we got ML in. Since they already exist in the abstract model, we call them the old events. But they are the abstract version. All right? And then these events are somehow inherited, or they are visible to the concrete world, in which case we have to somehow redefine or override them. So we got ML out again, and also we got ML in. Right? That's something we kind of did in the last couple of lectures. So they are the old events because they already exist in the M0, but they are the concrete version. Concrete in the sense that they are basically modifying the A, B, and C concrete variables as opposed to abstract variable, right? So just put you in the context. We got N here, and we got A, B, and C here, all right? A, B, and C, all right? Today, we're going to say something new called new events. The events only exist in the concrete model, okay? So new events. So for the new events, you don't really say they are abstract or concrete. They only exist in the concrete model. Of course, you can say they are concrete, but you don't need to. Just say new events. So we got IL in. and also IL out. And we're going to talk about them right away. Okay? And for your information, here IL stands for island. Okay, island. Into the island, out of the island, basically. Okay? So in total, we got 4 events to worry about for M1 in total. And once we introduce the new events, we'll see that there will be some potential risk that might be associated with the new events called life lock or divergence. That's something I would like to at least introduce today. And then once we talk about what life lock or divergence really means, when the new events might cause them, we have to see how we can somehow state the corresponding proof obligation to really show that they don't really exist, right? So that's something we got to do. All right, let's take a look. Okay, let's see the slides right here. So we start with slide number 68, right? So this is where we are. Okay. So we talk about concrete events or new events. IL in, IL out. Let's talk about the first one, IL in. Okay. And this one simply means a car entering the island. So let's see exactly what that means visually. Okay. So if you look at this diagram here very quickly, right? So before we already talk about ML out over here, and also ML in. These were the 2 events we were talking about, right? And then we also got a concrete variable measuring the number of cars. We got A here, we got B here, and also we got C, right? A will be this direction, and C will be this direction, right? So you can also look up the updates by ML out, ML in. That's from before, okay? So today we're going to see ML out, for example, simply means one car is actually heading to the bridge. It's on the bridge already. At some point, the car will be on the verge between the bridge and the island. So now, as soon as it got into the island, we're going to increase, of course, the value of B. In that case, the occurrence of IL in is going to happen, right? It's just about one car going into the island from the bridge. All right? So that'll be the first event we're going to see conceptually. Okay? So this will be from bridge to island. Okay? Symmetrically, if some car from the island, they actually want to go back to the mainland. Of course, first of all, they got to exit the island to the bridge. So this will be from island to the bridge. Okay? So these are the 2 events we're going to see. And let's see, they are very easy to specify, but we can still talk about a little bit about logic there, just to revisit similar issue that we faced before. Okay, so let's look at IL in right here. Okay. Oh, how about we just look at the GAR first of all. Sorry, not the GAR, action. Let's look at the action first, and then we might be able to somehow think about accordingly how the GAR should be specified. Why don't we look at the action first? IL in simply means we are going to go into the island, right? So now, what do we change in this case? Out of A, B, and C? A and B will be changed, right? Good. Because the number of cars in the bridge is going to be decremented by 1, and then number of cars here is going to be incremented by 1, right? Obviously. Okay, let's write it down. So this one here, we can put A will be A minus 1. B will be B plus 1. Symmetrically, if you consider this event right here, so one car will go from island to the bridge, so symmetric updates, right? So this one, I can also fill it out. This one means we got to decrement one car from the island. So B minus 1. And also C plus 1. Okay. Of course, what we have to somehow specify as GARs to make sure. For example, when you say you want to go from here to here, you better make sure there's no car coming this way. Otherwise, we got clash, right? That's kind of the GAR we have to kind of use to prevent any safety concern to happen. Okay, let's start with this one here. Okay, what kind of GAR should we have? What does that mean, really?
There's some car on the bridge approaching the island, while there's no car on opposite direction based on the existing event.
Okay, that's good. So this one here, A larger than 0 for sure. Let me write it down. You just want to interpret that, right? Otherwise, this. So this one here, for sure, we need A larger than 0. You got when you say there's one car going from the bridge into the island, there's got to be at least one car to be that car, right? For ILN to really happen. So that's why A should be larger than 0. You also mentioned about C equals to 0, right? Okay. So now we are facing a similar design issue here. Let me put number 1 here. Okay. So now number 2, you're suggesting or putting a different color. C equals 0, which I agree conceptually because we are saying that if you're going this way here, make sure there's no car going this way, right? Yeah. Now the question is, I agree it's correct. It makes sense. But is it really necessary? No. No? How come?
Oh, I had a different question, but...
Okay, let me handle this one first and I'll get you a question. Why is that not necessary?
On the P is just invariant 1 5, A equals 0 or C equals 0. So now we know that A is larger than 0, therefore we can imply that C equals 0 is by simple proof of behavior.
Right. Right, so guys, I think for this one here, I think fellow student is right. When you look at this one here, the question is, this is correct. However, is it really strictly necessary? The answer is no. So you can refer back to the guard that let me just go back there, just to be 100% precise. Bear with me. When we first spoke about the ML out guard, maybe back last week, okay, I'll show you directly. Bear with me, right here, right? Before, we had basically ML in, that's the one. We were asking whether or not it's necessary to put A equals 0. And then our conclusion was, well, it's more like an exercise, right? But the conclusion was, it's actually not necessary because you are able to somehow use the existing guard and some relevant invariance to show that this extra guard is simply derivable from what we had. So you don't really need to specify that explicitly. So now we are facing a similar situation over here, all right? So just make sure you revisit MLN. These two are kind of related. Similar concern for the design. Okay, let me go back. So when we go back here, we're asking a similar question. I'm going to put it down. Is this guard here really necessary? Okay, I will put it here. C equals 0. Is it really necessary? It would be necessary if the existing guard that we already had, like A larger than 0, together with all the invariants, cannot really entail this particular guard. In that case, we kind of put it there explicitly. If the existing guard plus the invariants already entail this particular C equals 0, then we don't need to put it, right? That's the kind of thinking process. So as last time, I'm going to put a little exercise here for you, all right? That should help you formulate the concern. We know that A larger than 0, which is right here, right? The first guard that we agree. And also we got the invariance 1, 5 right here. Either A equals 0 or C equals 0. Does that entail C equals 0? Okay. So given that you already finished your written test number 2, I think that this one should be a very simple thing to really see if that's provable or unprovable. Okay, I'll leave that to you. All right? Anyway. Okay, so 1 for sure. And 2, you can see whether this sequence here is provable. If it is provable, you don't need to put it explicitly. If it is not provable, then you better put it. Okay, just like that. Okay. So that's for IL in. Let's now look at IL out. That one there is really about this way, right? IL out, right? So we got to make sure there's at least one car in the island. Otherwise, there's no car to really exit from the island, right? So that one there, we're going to put also number 1. Number 1, we're going to put B larger than 0. At least one card for us to really decrement. So we got one card leaving the island. Now, what else? If the car is actually going to go this way, we also got to make sure there's no car coming this way, right? Okay, that's exactly what you want to say, right? So now, again, similar question, right? If I put number 2 over here, we got A equals 0. Now, again, similar question. Is this guard necessary? Or put it another way, do we have enough hypotheses that's already there to show that A equals 0 is provable?
No.
Okay, I can tell you that it turns out no. All right? So, for example, what you can try is this. Okay, this one I can tell you. Because when you see the final version of the first refinement, you will see that A equals 0 is actually there. Okay? So you're going to formulate this into another sequence right here. You can put it here. And then put a turnstile. You want to show whether or not A equals 0 is provable. And the first part there, you should really put all the invariants. Okay? All the invariants. Okay? So you just put all the invariants. And then you're going to put the existing guard that we agree. And also B larger than 0. Do they entail A equals 0? If they don't, you better put A equals 0 there. Right? Again, so this kind of process here is actually very valuable just for you to make sure you know whether a particular guard is really necessary. Okay? Question? All right. There's another insight. Oh, sorry. Go ahead.
For the number of invariant preservation proof obligations,
Yeah.
does it depend on the number of actions of the event or just the number of events themselves?
Okay. The question was, for the number of sequence we want to generate for invariant preservation, does it depend on the number of actions?
Yes.
It doesn't. Okay.
But do you just end the
Yeah. So okay, action here. Okay, that's very important. Okay. When you look at these two actions here, right, you don't really consider them as individual action. You can think about they get executed more like a transaction, which means they should really get executed at the same time. So that's why, remember the swap example that we did earlier, right? So you just can, for example, you cannot say A is A plus A minus 1, and then A becomes, let's say, A multiplied by 2. You cannot do that. You change every variable for at least exactly once. Right?
Is it still the same number of sequence, like for example? Like you know how we could prove invariant preservation, it's like A minus 1, we'd have to prove that A is still a natural number and A is still
So yeah, so for invariant preservation, it only depends on two factors. Number one, how many invariants do you want to prove? In this case, you got 5. Okay? And then, how many events do you have that might have the risk of violating the invariant preservation? For the new events, we got either this one here or this one here. So you got 2 times 5, 10. That's actually set in the slides. Okay? Question?
So for like the exam, when we write our guards,
Yeah.
we add an unnecessary guard. Would that be incorrect or would that be correct?
Okay, so what? Okay, let's. If the question itself is to say now, I could put an open format to say, okay, now specify the guard for ILN, for example. In that way, if you, of course, what's really necessary would be A larger than 0. But if you also put C equals 0, that's okay. It's just not necessary. Okay. I might also ask you to say, oh, given that this event is here, so is it necessary for me to add this particular guard? In that way, you have to justify, right? Okay, yeah. Any other questions before I point out some insights for us? All right. Let's now look at the actions for these two events because they're going to help us to understand how we can relate back to the abstract model. Okay. I want you to look at right here. Let's look at the first one. Okay, right here. Let's think about the pre and post states for this ILN. All right? So in the pre states, we know that invariance 1, 4 should be the case. Right? Invariance should be true before the events. Okay? We know that A plus B plus C equals N. And then, what about the post states? In the post states, we still have this pattern here. A, B, and C together should be N, except it should be prime, prime, and prime. Now, what should be A prime? A minus 1, right? B prime should be B plus 1. How about C prime? C, right? It's implicit, right? Very good. Okay, so let's write it down. Okay, so now I'm going to have A minus 1 plus B plus 1 plus C. Now, without a calculator, can you tell me what that is? Yeah, just A plus B plus C, right? Still, because plus 1 minus 1 cancel out. What does that tell us? It tells us, basically, the value for A, B, and C in the pre and post states for this concrete event is such that the corresponding abstract variable n simply has no change. It's a very important insight. It's as if we did nothing in the abstract world. All right? Remember, we said every concrete event should really have some corresponding abstract events. Okay? So that's something I'll get into a little bit later. Okay? Let me put down this insight and then we'll do one more. So here, if you look at these two, that means this will be as if nothing happened in M0. So as far as M1 is concerned, we have ILN happening. But for M0, the corresponding abstract model, it will be as if nothing happened. All right? Very important insight. Right? Okay, let's see one more. And for this new events over here, we got this here. All right? Again, let's do the comparison. Pre and post states. Pre, we got A plus B plus C equals N, corresponding to this invariance. In the post states, A prime equals A, right? Plus B prime, B minus 1. Plus C prime, C plus 1. That one is also equal to N, right? Plus 1 minus 1 cancel out. So this one here, we can also make another conclusion. N and also N. Okay? So similar idea. And then I'll make it more general. So this one here, and that one simply correspond to this one as well. Okay? So this is the general observation, basically. And that's going to be true for any new events you have to introduce in a concrete model. Every new events that we introduce in a concrete model that does not exist in the abstract model, they should be corresponding to something called skip. It's like nothing happened in the abstract model. Each new events in a concrete model should be simulated by an events of no change in the abstract model. Okay? And here, when I say no change, there is a special event which we're going to see. It's called skip. A little bit like this. Remember, in Java or in C, if you put a simple semicolon, null statement, doing nothing, a little bit like that. Or a method that simply got empty statements as a body, right? Okay. Okay, let me read it out again, just in case you're taking notes. Each new event in a concrete model should be simulated by an event of no change, which we'll call skip in the abstract model. We're going to make this more explicit just in a moment. Okay, I want to just show to you, since now we talk about the actions for these two new events. Okay. All right. Very good. Simulated by right here. Okay. Okay, let's talk about something very straightforward, and then we'll move on. Okay. Yeah, before after predicate. Yeah, this one here, very straightforward. I just want to mention very quickly. So here we say A and B. We didn't mention C. A prime equals A minus 1, and B prime equals B plus 1, and C prime equals C. Right? Very straightforward. Okay. Nothing else. Let's now talk about invariant preservation also very quickly. Okay, so invariant preservation should be should be the case for both the old and new events. So invariant preservation right here. Okay, So this should be the case for old and new events. And first of all, how many do we need? Since we got 2 new events, also got 5 invariants. So 2 times 5. Okay, you will see also this calculation on the slides. 2 times 5, which is equal to 10. Okay, and this is the proof obligation rule. Okay, so we got axiom, we got abstract invariance, we got concrete invariance. Guys, do you remember what this is? Concrete guard, right? Exactly, because we'll talk about concrete event, right? Like new events. And then that should really, and what about this? How do you interpret that?
Each abstract invariance.
Each abstract or concrete?
Oh, sorry.
Each concrete events in the post states. Because over here, this is about the effects, right, of the concrete events. Okay, be careful. All right, let's now see exactly how we can do this, right? So just this one here, that might need a little bit more reminder. So this one here will be each concrete invariance. Each concrete invariance in the post states. Okay, post states. All right. Let's now do just one of them. Okay. Let's say, how do we specify the sequence saying I or n right here should preserve invariant 1, 4, right? Let's look at that. And this one will be exercise for you. Okay. Let's look at that. So now we are focusing on invariant 1, 4, which is right here. And then we are talking about I or n, which is, okay, let me use a different color. I or n, which is right here. And we got a concrete guard. And also we got a corresponding action, which will help us to actually express the post-state version of the invariant, right? Okay, let's now do that. So according to the rule, we're going to do, first of all, we have axiom. Okay, this time I have it right here, axioms. So we're going to put the member of natural number, d larger than 0, straightforward. And then we have the abstract invariance right here. So here we got n, natural number, and also n less than or equal to d. Okay, that's the abstract invariance in the pre-states. And also we have the concrete invariance in the pre-states, everything. Okay, is going to be everything here. Okay, that one there, let's write it down. A should be natural number, B should be natural number, and C should be natural number. A plus B plus C equals n, A equals 0, or C equals 0. All right, one more hypothesis, which will be the concrete guard for the event we're talking about, I or n. So that will be the concrete guard. I or n has this guard, just one. Okay, A larger than 0. So that's all the hypotheses. You got to state that, right? And then we have right here. So this part here should be the post-state version of the concrete invariance. Let's now specify again something that's kind of intermediate, right? Since now we are talking about invariant 1, 4, A plus B plus C. So A prime plus B prime plus C prime equals n prime, right? And one thing to also remind you, okay, so we have to look at the abstract version and the concrete version. Okay, I'll get there in just one moment. So this is the effects on the abstract model. Okay, you can look up the component that we spoke about earlier. And also F over here is the effects on the concrete model. Just a reminder. All right. So now let's try that. So we can see for the A prime and B prime and C prime, that will correspond to the before after predicate. So before after predicate here will be A prime equals A minus 1, B prime equals B plus 1, and C prime equals C. Right? Okay, let's do the replacement. A prime should be A minus 1. B prime should be B plus 1. And now C prime should be C. What about N prime? Typically, if you want to find out N prime, what we did earlier was you have to go back to the corresponding version in the abstract model to find out the before-after predicate. For example, MLL or MLN. But in this case, there's no abstract version for ILN. So that's why I kind of show you before, we kind of work out. Before we actually saw that the ILN here, N has no change. So N prime equals N. All right? Okay, that's very important. Okay. So here we can just do something here. ILN. So here corresponded by skip events in M0, which will simply do M prime equals N. Okay, that's what we have. Okay, so that one there will simply replace M prime here just by N. So overall, let me write it down again. A minus 1 plus B plus 1 plus C equals N. So that's the final form you want to put as a goal. All right? All right. The other one, very similar. So let's assign that exercise for you, but you can also find the answer on the slides. Okay, exercise. So on the exam, there are different ways I can ask for this kind of like a basic question here, like a basic exercise. I can say maybe just give me the entire sequence without any simplification. Right? You just got to make sure you don't have any prime version of the variable. Or I can say just give me the hypotheses, or just give me the goal, right? Things like that. Okay, and then prove it, right? Right, if you look at that, you can also, okay, so there are two proof obligations. You can take a look. It turns out this is extremely trivial to actually prove. You will see. You just got to do some arithmetic to simplify the goal. You will see it's very obvious how it can be proved. Okay, I'll leave it to you. Okay, these two. Okay, guys, any questions? All right, so now I think we are done with specifying the two new events, ILN, ILL, have some basic understanding about their action. And let's take a short break, and then we'll talk about lifelock divergence after the break. Okay. I forgot, I want to do one more thing before we get to lifelock and divergence. Okay, this one very quick. Just to show this commuting diagram again, but except we're going to see how the new event is going to have its correspondence. Because, you know, for ML, you got a concrete version simulated by the abstract version. What about ILN, ILL? They don't have really like explicitly defined events in the abstract model. So let's see exactly, okay? So here is the principle. Each new event transition, for example, we got ILN and also IL out, right? Manipulating the concrete variables. So they are simulated by, okay, or also corresponded by certain events in the abstract world. Okay, so we call this a dummy events, like a dummy, right? It doesn't do anything useful. We just do nothing, basically. Okay, so this is abstract dummy state transition. Okay, this is what we call a skip events. Okay, you will see exactly the skip right here. You simply got empty action. It doesn't do anything. You know, for example, in our M0, you simply do M prime equals N. Just do nothing, right? But since anything that doesn't need to be changed, it doesn't need to be mentioned. So it will be just left as empty, okay? So it's a skip, and then it will be as if we said the V prime will be V. The post states will be exactly the same as pre-states. No change, really, all right? Every new event should be simulated by this hypothetical imaginary events that we don't explicitly declare in the abstract model. That's really the new information we learned today. Okay? Let's see how we can complete a computing diagram. And then we just do one little transition right from here. And I'll give you some quick exercise to try, okay? Maybe after today's class. Okay? Let's start with here. Oh, by the way, another thing to see, skip here, what should be its guard when it has no guard? True or false? True. Skip is always enabled, so it should be true. All right, so guard should be just true. Okay, okay. So let's now start with, for example, ILN. So let's say, for example, if I try to do some concrete events over here, let's say that's ILN. And then, so this is the states where you might be wondering, given that we have the skip events over here, is it really necessary for us to discharge the guard strengthening proof obligation for new events? Let me pause here, right? Let's think about logically, right? You might be thinking, we did guard strengthening for ML out and ML in. We want to make sure the concrete guard implies the abstract guard. But why? I can tell we don't really have any proof obligation for guard strengthening for new events. Why is it? Why is it not necessary? Say it again.
Because the true, of course, have a bigger scope than you have a guard.
Okay, that's good. Okay. It's not because guard strengthening is not really necessary for new event. It's simply because it's trivial to prove it. We don't even bother. Okay, let me show you. Okay. So think about over here. So this will be the concrete guard. Let's say just H, right? Oh, right here, just H. And over here, the abstract guard over here, in this case, it will be the guard for skip, which is just true. Which is the guard of skip. And we know that P implies true is equivalent to true, always. Is a zero of implication, right? So this tells us that guard strengthening is trivially proved. Guard strengthening. Trivially proved for new events. Okay, very important. All right. So this one here is also enabled. Okay, so we will be able to also take the transition for skip right here. Okay, so think about this one here. It's just going to be skip, doing nothing for the abstract variable. And of course, both of them should be related to the pre-states here and also the post-states and post-state over here. They should be, again, related to by the concrete invariance, especially linking invariance. So this will be the pre-states. And this will be the post-states. And specifically invariant 1, 4. And also invariant 1, 4, prime, right? It should really hold in both cases. Okay? Just to clarify about the computing diagram, still apply, just a little bit in a more like a special case where the abstract transition there just skip. And this is something we did earlier. So we said that after the init, so we'll go for ML out. So n is incremented from 0 to 1. And also A here, after ML out, is incremented by 1, right? That's what we did earlier. Okay? Let's just see very quickly. If we take one transition from here, so you can think about, naturally, after ML out, one car is on the bridge. Let's say the next event we're going to take will be for this particular car to go into the island, ILN. Let's say we do that trace. All right? Let's say that. Okay? So let's say the trace we're considering. First of all, initialization. And then we got ML out. And then followed by IL in, okay, etc. So one car goes to the bridge, and that particular car goes to the island, right? There's a sequence over here. Let's now take a look at how things are going to work. So from here, after ML out, we're actually going to get IL in, all right? And that one there is going to give us a post state right here, right? The D remains to be 2. And we also got A, B, and also C, right? So if you recall, for ILN, which is going to go this way, we are going to decrement A, increment B, right? Remember? Okay. So we're going to decrement A from 1 to 0, increment B from 0 to 1. C remain the same, right? Just according to the definition. Okay, that's good for the concrete transition. So now, for the abstract transition, we are just going to do the corresponding one, which will be skip. Right here. Just skip. And then we're going to have a post states in the abstract world. D remains to be 2, constant, and right now should be still 1. Still one car in the bridge island compound, right? 1 here. So now, are these two post states consistent? We're going to check the linking variance. So what we do is we're going to link these two right here, and then we check to see the invariance 1, 4. Okay, it should be A prime plus B prime plus C prime equals N prime. Right? So you just do the math. 0 plus 1 plus 0. 0 plus 1 plus 0. Is it equal to 1? Yes. So we are still good. So this one really shows to you, in the concrete world, we do the new event transition. In the abstract world, we do the skip, like a nothing, like a dummy events. And we still got consistent post states according to the linking variance. All right? So that one there is going to be 0, 1, 0. And that one there remains to be 1. Okay, still work. Okay. Okay, one more thing I want you guys to also try. Okay, so this will be a very typical events trace to really understand how things should work. So I'm going to put it down here, and you can give it a try. Okay, let me copy this diagram here, and then put it here. And then we talk about life lock. Okay, I'll put it here. So the idea is, let's say we have a single car. Okay, we want to somehow say the car somehow start in here, in the island. And then the same car moves to the bridge. And then it moves to the island. And then the car decides to go back to the bridge. And then eventually go back to the mainland. Right? Just the same car, really. Just do a round trip, really. All right? How do we specify that as a trace? Okay? So that will be exercise for you to try. I'll write it down. Exercise. So show the abstract and concrete transitions of, okay, so this particular trace, okay. So we're going to talk about concrete transition and also abstract transition, okay. So concrete transitions. And also, oh, you know what? I should put it in a little bit below, right here. And also we got abstract transition. Abstract transitions. We already did kind of a part of it already in this example here. Oh, so here. We can already started you with something. Init followed by ML ILN, right? We already did partially. But let me specify completely right here. Okay. So in the concrete version, let's see. We should really do, first of all, init. That one there should really correspond to init right here. That's good. Okay. And then in the concrete, we're going to do ML out. ML out. That one has the corresponding abstract version. So we're going to do ML out as well. All right. And then the concrete is going to go for ILN. The car will go into the island. Okay, ILN. That one there, as we show, it should correspond to the skip events. Right here. After that, the car will decide to go back to the bridge, heading back to the mainland. It's going to do IL out, which again should correspond to the dummy events in the abstract world, which will be skip. All right? And then finally, that particular car reaches the verge between the bridge and the mainland. So we'll take ML out, sorry, ML in to go back to the mainland. Because that's like a one cycle for a single car, basically. So that one there is going to be ML in. And then that one there is going to correspond to the abstract version of the ML in. Okay, try to see if you can just sketch on the paper just to see how you can show the corresponding events that kind of happen in parallel between the abstract and the concrete. And also, very importantly, is for you to observe the changes on the variables, the ABC versus N. And they should be somehow related to by the linking variance 1, 4. Okay. Okay. Exercise for you. But we'll do something also similar when we want to talk about invariance and variance. Yeah?
Yeah, I have a question, but I probably not related to that. But
Go ahead.
Is that fair to say that for any model, if the initialization proof obligation fail, it could only happen when the invariant are contradicted to one another?
Say it again. So I'm
So
not.
for any model, if the proof obligation of an initialization event fail, could only occur if the invariant are contradicted to one another.
Not necessarily. So maybe your invariants are completely correct.
Okay.
It's just the values you can initialize the variables into. They don't satisfy the invariance. It might be the case.
Yeah, because from what we see, we just put a random value.
Right.
So I just put a value that satisfy the typing invariant. For example, that you should do its job, right?
Mm-hmm. So put it this way, you can think about, again, the analogy would be like a mathematical induction, right? So you kind of state your inductive hypothesis to be something.
Yeah.
And then the initialization is just about proving them base cases. So base cases are just some concrete small value you want to show the inductive hypothesis will hold. And then once it holds, you want to show that all the inductive step that's going to follow.
The smallest value you are saying that should be related to the typing invariant?
Typing invariance definitely part of the invariance. You want to make sure they satisfy, but also their safety invariance and also the linking invariant as well. They all should be satisfied. So you got to choose your initial values for the variables carefully. So all of them will be satisfied.
So for one initialization, we should pick the value that is a base case.
Yes, yes. And usually the initial value you will pick for the variables are rather simple value. For example, 0, empty set, empty relation, things like that. Doesn't need to be always 0, but usually should be some simple value that makes sense for your application.
Okay, all right, thank you.
Yeah, okay, good. Not exactly irrelevant, but kind of relevant, okay. All right, let's now talk about lifelock divergence. At least we can see some example, all right? So for this particular model, I did some changes to the new events, okay, very quickly, okay. ML out here, ML in, they stay the same as before, okay. So these are the old events, but concrete. You know what? I think this one can be drawn a little bit better. Right here, good. So that's the old events. And then these two are the new events. And the changes I made is I took out their guards. There's no guard for these two events. That means they're always enabled. Okay? The new events over here, always enabled. From our initial model M0 there, remember we kind of started ML out, ML in to be godless, like always enabled. We know that it's not a very good idea to have some events always enabled. So now we're going to see another scenario where this could be very bad. All right? So to really, can anybody kind of see what might be an issue here when IL in, IL out is kind of like a godless? Of course, if they're godless, that means somehow IL in and IL out can always happen, right, without.
Or the values can be negative.
Yeah, exactly. Because you can keep saying IL in, IL in, IL in. Yes, that's one thing. What about another thing? Let's say somehow I do IL in, IL out as a loop. Somehow the value never go negative, but still we get an infinite interleaving between these two events. Right? That's the kind of the thing I'm talking about. Let's see. Okay. Let's try to see one scenario that's kind of problematic. Okay. Let's see a possible scenario that is problematic. Okay, let's see that. And let's see in the concrete world first, and then we'll see what a corresponding abstract transition sequence will look like. Let's do these two. All right, let's start with the concrete one. The concrete transition might be something like this. Concrete transitions. Oh, at the same time, let me just also get prepared. Let me also get this diagram ready, right? We might need that for visualization. Okay, I'll put it here, right here. One moment. Okay, fine. Okay, let's diagram there. And then for the concrete transition, let's say we still got our init and also ML out. All right? So that means we actually got one car to the breach. And then, let's say for the same card, somehow it decides to somehow go to the island, back to the breach, go back to the island, back to the breach, go to the island, back to the breach. It's drawing a circle. Is it allowed for this model here? Yeah. IL in, IL out. Just keep looping. All right? IL in, IL out. IL in, IL out. And infinitely. I'll take a question just one moment. So this scenario here basically is a possible scenario where that single card can simply do something indefinitely, where nothing useful can happen at the same time. It basically is blocking the system from functioning normally. Okay, question, please.
So I thought that we were assuming the breach to be one way, right?
Uh,
If the car goes IL out, then it should first reach the main line.
Yeah, good question here, because there's only one car. So there's only one car in the system right now. So as soon as the car actually goes here, there's nothing here. So we can definitely go back here. As soon as we go here, there's nothing going this way, so we can go back. So the guard is actually going to work. Yeah, you see what I mean, right? Okay. So this particular sequence over here is possible where the system is not really deadlocking. The system is still working, but not in a way that's very useful. Okay. So let me write it down right here. Okay. This is basically an infinite interleaving of new events. And they are not really contributing something useful to the system. Not contributing something useful while preventing other events from happening. Okay, it's a very important insight into here. So this kind of a scenario is equally bad as a deadlock. When we talk about deadlock before, deadlock simply means no events can happen. Your system basically cannot make any progress. So here, your system is always making progress, but the progress is not leading you anywhere. It's just about this particular weird car just driving a circle, and then nothing can happen really. But as long as such a scenario is possible, you got to be careful for your system. All right, that's one thing. So now question is, how do we see the corresponding abstract transitions? That's something interesting to see actually, okay? Let's now draw the corresponding abstract transitions. And for that one there, you can also easily draw some analogy. Okay, let me just put it down here. So here, init correspond to init. Emma out also correspond to Emma out. And question for you. In the concrete world, we actually see an infinite interleaving of the new events. What about in the abstract world? What do we see? Skip, skip, skip. You basically got skip indefinitely. It will be as if you write something like in 2031 or 2032. While 1, like that. Busy looping. You're not doing anything useful, but the computer is still running, still draining your resources. Nothing useful. All right? So this one here is analogous to what we have right here. Okay? Let me recap. Okay? So we got about 7 minutes. I can still do something very quick, but let me just say about what I'm trying to say here. You got to be very careful when you design your new events right here. Not necessarily just the guard, but also the action as well altogether. Whenever you're dealing with a refinements where you got new events, the new events simply correspond to skip events in the abstract world. You want to avoid any possibility of having the new events running into a loop that's going to loop indefinitely. In that case, it will simply correspond to an infinite number of occurrences of the skip events, which is corresponding to the busy loop, which we know is definitely very bad for your system. It's not deadlock, but it's actually doing something always, but not very useful. It's called life lock, or the system called divergence. Okay, the term will be, we say that the system, there's a life lock. Okay, so we say this is a life lock. Or we say it's a divergence. Or we can say the system diverges. Okay, you can go either way. Okay, so that's a term we're learning. You'll see the definition also on the slides as well. All right, so now how do we solve this problem here? Right, there's no magic, right? We still have to go back to our kind of a workflow, right? The way we kind of detect that there might be a possibility of the invariant not being preserved is to really try out the proof obligation and see if there's any unprovable sequence, and then go back there and fix the model, regenerate the sequence and prove again. Similarly for deadlock freedom. So here as well, to really somehow prevent us from having a scenario like a life lock or divergence, we have to introduce ideas called variance. Using that thing to really measure your system with respect to life lock. So we have to learn about another proof obligation to see how we can state the proof obligation. Okay, let me just say something here very quickly, and then we're done. Okay, let me just see here. Okay, let's now do just one page. Okay, very quickly. So far we talk about life lock. And or divergence. Right here. Okay, let's remind ourselves Lifelock or divergence is caused by an infinite interleaving of the new events. Caused by an infinite interleaving of new events. And you can think about this, this will be as if BC looping. In the abstract model. So what we'll see on Tuesday. Let me mention this bullet point here very conceptually, and then we're done. Okay, give me 4 minutes. Okay, what should we do? We want to introduce something called variance of the system, rather than invariance, which really stay true all the time. Variance is going to be some expression of type integer or natural number that's always going to change, the opposite of invariance. All right. So we have to use a concept of system variance. Or sometimes we just say variance. And the variance is some expression of type natural number. Okay? And some important concept about the variance. So here, variant here, this is not a solution to lifelock. Instead, it's more like a measure to detect the presence of lifelock. Instead, it is a measure of the number of times new events might interleave. Okay? And when we say the number of times over here, if the number of times, we want to make sure it's not infinite. There's a way to really make sure it is not the case. If that's infinite, that's not good. If it is finite, we are fine. Okay? And then there will be two proof obligation. Two proof obligation to discharge. If unprovable, we should go back to the model and fix it and regenerate the proof obligation and then regenerate, right? And then prove again. If unprovable, fix the model. Right, so we're still following a similar workflow as before, like a de la Frieden and invariant preservation, right? So before next Tuesday, please make sure you kind of revisit about the possibility of lifelock, and then we'll talk about variance and also see the proof obligation. All right, thank you so much. I'll see you on Tuesday.